We now welcome Dr. Oliver Curtin, who will talk about Ettore Majorana, the troubled genius of the nuclear age who disappeared in mysterious circumstances in 1938. Oliver obtained a master's degree at Imperial College, London, specialising in string theory. His PhD focused on quantum properties, quantum impurities, and the emergence of Majorana Fermions. Following a period as a visiting researcher at Imperial, Dr. Curtin joined Morgan Stanley as a quantitative strategist. Please welcome Dr. Oliver Curtin.
Thank you, Suzanne, for that lovely introduction. So today I'm going to be talking about Ettore Majorana, his origins in Italy and some of the work that he actually did in engineering and physics, as well as some of the mysteries surrounding his disappearance and his ongoing legacy in science. So he did a number of very cool things back in the 30s at the start of the nuclear age. So in particular, he's famous for the development of the theory and the theoretical framework behind neutrons and their discovery, and also a special type of particle which we don't know strictly whether it exists in the universe, and there's a lot of active research trying to find out whether it does, and that's the Majorana Fermions. And as I mentioned, we'll talk about his disappearance and his legacy. So he was a Sicilian-born physicist / engineer, and he started university when he was still relatively young, at age 17. He went in as an engineer, and he must have been very good at it, and he must have enjoyed it because he stuck it out for 5 years. But he had a natural mathematical talent, as well as a physics talent, which was noticed by one of the senior physics academics, Emilio Segre, who is pictured on the slide. And following Segre's advice, Majorana actually switched to physics in 1928. So he was very well established by then as an engineer, and he sort of started out something new. And the first thing he worked on was atomic spectroscopy, which was a big deal at the time. And what this has to do with is, if you imagine like an atom or some kind of low, very low energy, small object, and you're going to illuminate it with radiation, you actually get radiation spat and churned back out at you. And the study of spectroscopy is kind of an analysis on the different energies, well, the different kinds of light you can get shining back at you and their energies, and where they sit on some kind of spectrum. So what you can, so it's kind of as shown on the slide. You can imagine a quantum state as being very discrete. So you've got a lower energy and a higher energy, which are respectively E1 and E2 on the slide. You can illuminate your system with some incident radiation and excite, say, an electron or other particle which is bound in the state. Of course, when something is in a higher energy state and there's nothing below it, it's actually unstable. So it will drop back down and emit some radiation, which is sort of what we see here. And this is kind of what's going on. So he's looking at the outcoming radiation and he's saying, right, what can we determine about the systems? And it turns out you can determine an awful lot. So this is, for example, how the northern lights work, and your different colors of the northern lights will depend on the different energy states in the different atoms which are being excited by instant solar radiation. It's also useful in the study of stars when you're looking at the material and chemical composition. So he became quite established in spectroscopy, and then he started asking questions to do with the real interior of the atoms, the nucleus, which is like the little green dot on the slide, which at the time was very poorly understood. So this was his step into the nuclear era. And he worked with a guy called Enrico Fermi, who's very, very, very famous physicist, most notable for his work in Project Manhattan, or Manhattan Project, and the development of nuclear weapons, as well as many theories of quantum particles at the small scale, such as Fermi liquids, sort of Fermi scattering and so on. And he worked on this scattering model, which is really about instant radiation or instant charged particles on an atomic nucleus. So the first thing he did, which kind of, it's kind of related both to the nuclear structure and to what his work on spectroscopy was, which was this thing called autoionization, where by virtue of having a temperature, electrons in atoms can just jump spontaneously between energy orbitals and emit or indeed absorb radiation. And through this, he sidestepped away from spectroscopy into the land of Enrico Fermi and actually joined his group, which called themselves Via Panisperna. They named themselves after the street that they were based on. I forget the name of the city. It was in Italy somewhere, and it was the building where Fermi's group sort of sat and contemplated nuclear physics. So he worked with a number of very interesting people, most of whom went on to work in the Manhattan Project. They did all sorts of things to do with neutron scattering and the stability of neutrons in nuclei. This image is actually a modern day application of some of the work they did. It's a nuclear reactor, and the small bars you see are actually boron rods which get inserted into the core and absorb neutrons. And in this way, you can actually control the rate at which a nuclear reaction actually occurs. So this is how we can safely generate electric power. But before this, there was the open question of, well, we're doing all this work in nuclear physics, or the nucleus of an atom, but we don't really know what's going on. There was this big problem at the time, which was that the nucleus could have one charge, but multiple different masses, and nobody really understood it. So there are a number of theories which came from Rutherford about 40 years before, but this property of different masses actually violated those theories. So it was a very big question at the time, and it led to a big revolution in physics. As a testament to Majorana's ingenuity and also modesty, he considered the solution to be obvious. He said, well, there's clearly a new type of particle which carries no charge. And he actually sat down and did the theory and proved it, and impressed Enrico Fermi enough that Fermi said, you have to publish this. Majorana considered it very obvious and didn't bother. Eventually, it was published by a guy called James Chadwick, who got the Nobel Prize for it. So Majorana kind of missed out a bit there. But I think it's quite nice. It's a very rare trait in physics to have such a combination of ingenuity and modesty. As nuclear physics sort of developed, so did a model and theory of the underlying universe, the quantum universe. And there was kind of a big revelation in like 1928, 1929 with Schrödinger and his famous equation. We've probably all heard of Schrödinger's cat. But that equation kind of had some like limitations, mostly due to whether it could describe relativistic states, i.e. when you have high energy or very fast moving particles, basically. Eventually, a guy called Paul Dirac, who's pictured, solved the problem. And he wrote down this equation, which is the only equation in my talk, which is a tremendously important equation. Known now as the Dirac Equation, it governs every single particle in the universe. If any of you ever look at an equation or the standard model, you'll see this equation dotted around everywhere for all the different types of fermions. One of the debates which is quite topical at the moment is to do with the distribution of matter and antimatter in the universe. We've all heard of, say, a particle and an antiparticle come together and they just explode. Basically, there has an enormous release of energy. And those particle states, i.e. matter and antimatter, come from this equation. You can imagine, I mean, you can see you've basically got sort of psi times psi on each side. So you've basically got a -1 invariance. In physics, you'd say it was Z2 invariant. We can think of it as being positive or negative solutions. The positive solutions will give you matter, and the negative will give you antimatter. This was, shortly after the equation was published, kind of accepted. You know, there was some There was some argument over whether antiparticles could really exist, but most people thought, well, probably quite a good equation even if they don't. Eventually they were found, so antimatter was confirmed. But Majorana was asking the question, well, we've got positive and negative, but what's zero? Is it positive or is it negative, or is it simply just something in the middle? Does it exist? Is there a zero mode? Because you could imagine, if you wanted to make this quantity very small, you could imagine setting psi to 0 and the whole thing would just disappear. And he worked out that actually there was a solution, and that solution was called a Majorana Fermion, which is a particle that is actually its own antiparticle, a very strange concept. The idea being that two of these particles would come together and then would annihilate kind of themselves. And you get some very funny statistics or sort of thermodynamics coming out of these sort of systems. So they are very, very strange particles. There's still a lot of debate as to whether they exist in the wild. There was some recent progress, maybe about 5 years ago, when they were actually manufactured in a lab in like a quantum metamaterials type system. So this was sort of coming up to about 1936, 1937, and it was the last paper that Majorana ever published. What actually happened was he got very depressed. He'd sort of traveled around Europe a bit, and he was working at the time with a guy called Werner Heisenberg, who was put under a lot of pressure by the Nazi regime. And it's quite possible that the rise of the far right actually influenced Majorana, or he just had mental health problems. But he became very depressed and withdrawn and isolated for a period of about 4 years. And he would be quite dismissive and rude to his mother, and his family relations kind of deteriorated over that time. So it was quite surprising that his work on Majorana Fermions actually was published at all, but he did after 4 years of reclusion. And then he sent this message to the director of his school where he worked, actually in Germany with Heisenberg. In it, he says that he's made an unavoidable decision, which he can't really, or which he really doesn't go into a great detail on. But he basically says, I'm going to disappear. And he makes a very strange comment that he will have a memory until at least 11 p.m. that night, which is kind of an odd thing to say. He followed up by withdrawing all the money from his bank accounts and decided to return to Sicily, and he actually bought return tickets there. So what people know is that he made it to Sicily and then never came back and was never seen or heard from again. So a very interesting kind of fate for a very brilliant physicist. There are a number of theories which were sort of dotted around at the time. His telegraph suggests suicide, which was kind of evidenced by his decline in mental health, as well as his indication that he would only have a memory which would last until 11 p.m. Also, many of his colleagues thought this was the most likely option. So by this time, it'd been 10 years now since he had started working on nuclear physics, and he was well known across the field as a nuclear physics expert, just as governments, particularly in the West, were looking at nuclear physics research and trying to weaponize it. So there are a number of theories surrounding possible assassination, or at least abduction, to remove him from the nuclear sort of playing board. There are a couple of witness accounts which survived at the time, suggesting that Majorana was seen in South America and he had gone and started a new life. They were sort of dismissed at the time, and the official investigation closed without any very well evidenced conclusions. But it turns out that he did appear in South America, and he was operating, or at least living under a false name, which was Denis. There were a number of photographs and character references which emerged nearly 70, slightly more than 70 years later, causing the Italian government to reopen their investigation. And they did find that he actually was present. And there are a number of locals who were able to provide witness accounts, who, at least character accounts, and those accounts kind of matched almost perfectly what the investigators were expecting given Majorana's A, brilliance, B, temperament, and C, personality. So they actually closed the investigation saying that he probably moved there voluntarily. It seems that he was working as a mechanic, so maybe there was a connection to his previous work or studies, at least as an engineering student. And nobody really knows what happened for the rest of his life, but he lived it in relative seclusion. So finally, my last slide is on his legacy and some of the research which he's inspired that lingers today. So firstly, neutron scattering, which is kind of what he worked on right at the start. We have a huge amount of technology now which we kind of take for granted that's based on these principles. So nuclear energy and weapons being the obvious ones, and certain types of imaging where we basically, fire stuff at atoms, break them into pieces and, see what comes out. You can build all sorts of spectra diagrams and stuff from that. Neutron stars have also been recognized to exist, and these are very dense bodies of matter which sort of sit far off in the universe, fully just completely made of neutrons. The Crab Nebula is a very famous nebula, and it's got lots of very beautiful pictures of it. Sitting right in the middle is actually one of these neutron stars, which are very, very dense, have very strong gravitational fields. So you can imagine like a gravitational well pulling things towards them. And I'm sure if you get close enough to them, you'd be able to see like shoots of matter spiraling inwards. But then we've come on to Majorana Fermions, which are hugely important in many different areas of physics. So in an abstract kind of way, what they govern is something called topological stability, which is where if you want to store information in a quantum state, the state is very unstable because you've got something very small and you might have a finite temperature. So it will quite quickly, what we call decohere, it will lose its information. It turns out that you can actually bind your states close together and make it very difficult for the state to fall apart, basically. And this is what we call topological stability. One very important application of that is quantum computers, where we want to build very powerful, very fast, very parallelizable computers to store a huge amount of data and process it, in ways completely different to a conventional computer. One of the key problems with that is this loss of information, which topological stability and the Majorana fermion can actually help. Finally, well, not quite finally, but along the lines of fundamental physics, we've got these neutrinos, which they're very weakly interacting particles which just propagate straight through the universe. They basically don't interact with anything. There are some awesome experiments going on in Japan, like Superkamiokande, where they have just giant wells filled with water and detection devices, and they might see a few a day. But the neutrinos actually change what's called generation. So in physics, you can class your particles. And normally, particles don't move from one class to another. Neutrinos are the only exception. And it's a big mystery as to why exactly they're doing this. And lots of people speculating, well, they could be facilitated by a Majorana fermion. Now finally, we have these metallic impurities and quantum metamaterials, which are, you can imagine, a very small, very precisely engineered quantum system, something made by a lab or in a lab by some kind of very precise machine, such as an MBE, molecular beam epitaxy machine, that will create a system with very carefully engineered properties, such as a nanowire in this case. So you could imagine just a plane of maybe gold atoms, and then just a line of maybe iron atoms. And you can get electronic modes which propagate along this wire. And those modes, it turns out, can actually have the statistics of Majorana fermions. And now this can be used to understand some very odd properties that you get in metallic impurities, when, for example, you might have a lump of a nice normal non-magnetic metal with some very small number of magnetic impurities. Like imagine if you just pulled a lump of gold out the ground, you would expect it to be impure, and you can get some odd properties arising from that, which are explainable by Majorana Fermions. And we also don't really know the kind of applications these systems would have, but we do know that they would have very precisely engineered properties which would make them metamaterials. So that's the end of my talk, and thank you all very much.